Hello, everybody. Thank you for having the chance to speak here. I hope it's not too late to talk about sophisticated optics. My name is Andreas Wegner-Berndt. I'm Managing Director at Vision and Control and responsible for the value chain and the product life cycle as well as the administration. Today I'm going to take a quite untypical approach. I would like to speak and inform you about very special optical systems, but I do not want to disclose too many details. That's why I used sketched principles and schematics for this presentation. So then let's start with a brief introduction of vision and control. Our vision is that our photonic-based solutions make machine seeing. We are a global acting OEM supplier of photonic-based solutions, and we support leading companies in their field, which are metrology, semiconductor, glass inspection, automation, and laser processing, as well as life science and medtech. Our know-how is characterized by a broad portfolio of technologies grounded on photonics and the unique nature of light. And a comprehensive catalog is kind of showcase of our technology and quality. So we are OEM and catalog supplier. Vision Control was founded 33 years ago in 1991, so we're looking back on a broad history, a rich history. And we are located in Suhl, and that's exactly in the middle of Germany. And our small team is very committed and experienced. And we do R&D. We do in-house R&D for optics, mechanical design, and also lighting design and vision systems. And as well, we do in-house production. We do quality made in Germany. Let's move to point 2 of our agenda, opportunities of tailored optical systems. And very often we see applications in metrology, semiconductor processing, and also analytics, which require special optical systems. And off-the-shelf optics often do not take too much progress compared to the requirements. And that's why customized optical systems allow them to make precise imaging of structures and profiles with less effort, to use limited space and cycle time for combined inline inspection modi, to focus on typical elements of the inspected objects, to visualize laser applications, to save space and time, and to make hidden details visible, or vice versa. Coming to the first example, lenses with very low depth of field and very high numeric aperture for precise height mapping. For the depth of focus applications, and what we see here is a typical lens design. In that area, we see a double Gauss lens system with magnification 2, with a numeric aperture of more than 0.2 on the object side, which is aperture f5. And as you can see, we see a very good resolution on the right side on this US Air Force target, and the the MTF chart on the left side. Coming to point 4 of the agenda, that are multi-aperture lenses. Here I used a schematic principle, sketched principle. Multi-aperture lenses, we are talking about if you have 2 or more imaging modi combined in one optical system. That can that can be, for example, very mixed applications of high resolution with sensor as in the APS-C format, in gas sphere sensor in the 2/3 inch format, like the IMX 99 something 990 I mentioned here, and as a third option, a polarization sensor. So that's a very that are very mixed application, but it's possible to do so. And we see on this sketched principle, we see the object on a belt. We see the distal optical section. We see the beam separation to the different imaging sensors, and all these sensors can be connected to one of our multi-camera vision system with brand name VisionSTR, and do the inspections in parallel, and this save cycle time, and this save also this save also space. Point 5 of our agenda is exactly the counterpart of what we have seen before. That's the multi-measurement lens, or just said split field lenses. Multi-measurement lenses are called if you have one image split it into 2 or more specific points of inspection of one object. You see it on the bottom side. For example, if we only want to inspect the edge or the flange outlines of an object, and what we see here are two telecentric lens systems, the distal part, and you see a beam splitting device, and for example a high resolution vis sensor in the IPS-C format connected to one of our VisionSTR multi-camera vision systems which do the imaging task. On the left side you see an example of such a beam splitting device, how it looks like physically. Point 6 is a very special solution for laser tracking. What we see here is a sketched setup that we use this solution if you want to track the laser to allow inspections around the operating range of the laser. It's for the combination with galvo scanners and f-theta lenses. And what you see here is on the right side you see a endocentric lens with a coaxial lighting coupling into the laser beam via a dichroic mirror, and focusing on in the f-theta lens reflected by the galvo scanner. Last but not least, I want to highlight two optical systems that we have in our portfolio and that we have already talked about in one of our previous presentations in that field. But I want to highlight it once more. There are optical systems for application in specific spectral ranges, for example, sphere optics. We know that every material has a different reflection of light across the electromagnetic spectrum, and at very specific wavelengths, material change from reflective to transparent and vice versa. And it can be used to identify materials and to make measurements in application where it is not possible to do these measurements in the visible light spectrum. At Vision and Control, we mainly apply optics in the vis to sphere range, and that's exactly the range where the most effects that I mentioned are applicable. One example of this optical solution is one of our blue vision lens is the TO66. It's an object size of 66 millimeters. It's for a 2/3 inch sensor that's meant with /11. And we applied the apochromatic correction to optically optimize for the vis to the sphere range. So via this apochromatic correction, it is corrected from 400 to 1,700 nanometers. On the right side, we see the chart of the focal shift over the wavelengths, showing the result of this apochromatic correction. Bottom right, we see the influence of the wavelengths to the work distance, and we see pretty low work distance adjustments. On the bottom left side, I added the diffraction MTF chart at the aperture of f14. On this slide, I added the principal layout and the distortion chart. The relative transmission of that optical systems is all over this range more than 80%, up to 1,700 nanometers. But the key for the best application is a specific coating in the field of the application. So it's in our opinion, it's more effective to the customer to have a specific coating as to have the widest possible, AR coating. Yeah, and the result would be that the transmission at the edges of the spectral range will be reduced. Our bi-telecentric lenses are originally designed for the vis and near-infrared spectrum and are suited to many applications in the sphere spectral range too. We have tested it. We have found very good results, and as we can see in the tables below, the work distance adjustment is low and way less than the depth of field of that lenses. For a better illustration, I want to show an example that I did with our TOB22. That's one of the previously shown wide-centric lenses in an electronic application. And as we see, what we see is that the solder stop layer is transmitting at 1,550 nanometers, and we can see the copper layer. So the copper layer is visible. And on the left side, we see a glass object at the melting point without any active lighting. And I want to highlight one more optical solution that are our large field lenses, which we show on our booth in hall 10, booth B87, and and these lenses are dedicated for inspection of big objects or whole assemblies. And looking at, we think that exceeding a front lens diameter of more than 200 millimeters, the cost, the height, and also the weight and the mounting effort increase dramatically and lead to a limited industrial usability. And looking at the principle of Fresnel lenses, on the right side we see that the projected lens radius is segmented and applied on a flat surface. Fresnel lenses are molded parts made of high optical grade plastics. And this Fresnel lens approach allowed to build lightweight designs for telecentric inspection of large objects. The biggest one that we did is nearly 60 by 60 centimeters, and we do also small wide field lenses for line scan application that can be customized. So that I hope I could spark your interest, and I'm open to questions.